Hello students, this is lecture number 13 and 14 of Signal and System course, and today we are going to discuss about a very important topic in signal and systems, which is Fourier series representation of periodic signals. So in last lecture we discussed about the response of linear and time invariant systems when input were complex exponential or complex sinusoids. So from that lecture we have some idea that the signals can be expressed as a linear combination of sinusoids, right? And it is more convenient to represent signals as a linear combination of sinusoids or complex exponentials because the eigenfunctions of LTI systems are complex exponentials. So when we have input as a complex exponential and eigenfunctions as a complex exponential, it is mathematically convenient to compute the response of the system, right? So this can be done as shown in this figure, that h of t is the impulse response, that is the system, and when x of t is any arbitrary signal which is represented as a linear combination of complex exponential, and it is given as the input and the response is computed. So either we can do this, or we can actually make use of a superposition property of LTI systems and compute the response of the system by giving each complex exponential component separately and then adding all the responses together. So this is one of the convenient way to compute the response of LTI systems. So the sinusoidal signals, the signals that we give as input to the LTI systems can be any form. They can be real sinusoids, they can be complex sinusoids. So whether they are real or complex, we can represent them in the form of complex exponentials. As for example, a cosine function is a real function that is represented as a combination of a linear combination of two complex exponentials. Similarly, sine function. So in this way we can actually represent any kind of periodic signal in the form of linear combination of exponentials. So the representation of a periodic signal by linear combination of sinusoids is called Fourier series, and it was given by Joseph Fourier, a French mathematician, very extraordinary person. If you get some time, you can actually Google his work. He has a lot of works in mathematics and science. Also, his life is full of adventures. You can actually Google his history and you can read about his life as well. So it is a very convenient tool for many engineering applications, right? And as far as the signaling system is concerned, it is a very handful tool to solve many complex problems. So continuous time Fourier series, or the Fourier series in general, is used to represent the signal in the form of linear combination of complex sinusoids. And also once you break the signal into the complex sinusoid, you can actually determine the contents of frequency components in the signal, or in other words, frequency contents in the signal. What kind of frequencies are present in the signal? Or simply we can say we can draw the spectrum of the signal very easily once we break the signal into the complex exponentials. So let us have an example to clearly understand what Fourier series means. So let us consider a signal x of t, which is actually, this is triangular waveform, or this sawtooth waveform to be precise. This waveform in the dotted line is actually x of t, right? And let us represent this x of t as a linear combination of sinusoids, right? So this x of t is basically a periodic signal and having period t, for example. So in Fourier series, what we do, we represent any one period as a linear combination of sinusoids, and since it is a periodic signal and it is repeating itself, that representation is valid for entire signal. Right. So we will take only one period, for example from t0 to t0 plus t, that is one complete cycle. Right. So we will take this one period and we will represent this one period as a combination, linear combination of sinusoids or exponentials, and then that representation would be valid for entire signal. So the representation of this x of t by a constant can be done by this line, right, 0.5. Right. So if for example, if you want to approximate this triangular waveform by a constant, right, so the best approximation would be a constant line at 0.5, which is basically the average value of this wave. Right. So this is the best approximation because error is minimum. If we approximate triangular wave with a constant having value 0.1, for example, then the maximum error would be 0.9. Similarly, if we approximate it by 0.8, then the maximum error would be 0.8. So the best possible approximation by a constant is 0.5, which is basically average value, or a constant is basically a sinusoidal waveform or cosine waveform with zero frequency. Right. So with this constant is basically 0.5 cos of 0. So this is representation, approximation of this triangular waveform by this sinusoidal signal. Obviously it is not accurate, but this is the best possible representation by a constant. Now if we want to increase the accuracy, we need to add more components, more sinusoidal waveform. This is only one sinusoidal waveform added in signal with zero frequency. So let us add another sinusoidal waveform along with the constant. Right. So we have added another waveform, and of the frequency same as the frequency of the triangular waveform added with the constant, and now you can see the approximation of the signal x of t is relatively more accurate as compared to the last one. Right. So as we keep increasing the sinusoidal waveforms, the accuracy of the approximation would keep increasing. For example, this one. Now we have added another sinusoidal waveform of frequency twice of the fundamental frequency. Right. Fundamental frequency is the frequency of the first sinusoidal waveform. Right. So now we have added another waveform, sinusoidal waveform of twice the frequency of the fundamental frequency. So now we have three components added. Right. A constant 0.5 sinusoidal waveform of frequency 1 upon t, and we have another sinusoidal waveform of frequency 1 upon 2t, 2 upon t. And when we add all these three components together, now you can see the approximation of the triangular waveform is getting accurate. Right. So similarly, if we keep adding sinusoidal waveforms of integral of frequency, which is integral of the fundamental frequency, we will get approximation more accurate. The accuracy of the approximation would be increased. So similarly, we have added another waveform which is 3 times the fundamental frequency, and you can see the accuracy is increasing. Right. So this is what the Fourier series is. Fourier series is that the actual signal, which is in this case is triangular waveform, is basically combination of sinusoidal waveforms of different frequencies. So for example, zero frequency, first fundamental frequency, then twice of the fundamental frequency, 3 times the fundamental. So when we all add all these sinusoidal components together, you get triangular waveform. So this is what the Fourier series is. So as the number of sinusoids approach infinity, the approximation can be exact. So when you add infinite number of sinusoidal waveforms together, you will get exactly same as the triangular waveform. Now let us consider the equation given here. Phi of k of t is equal to e power j k omega naught t, where k is equal to 0, plus minus 1, plus minus 2, and so on. So these are actually expressions for harmonically related complex exponentials. Right? Harmonically related means their frequencies are actually multiple of each other, integral multiple of each other. For example, at k equal to 0, phi is equal to 1, right? And k equal to 1 plus 1 or minus 1, phi 1 of t is equal to cos omega naught t plus minus j sin omega naught t, right? And similarly, when k is equal to 2 plus or minus 2, we have another sinusoidal form having frequency 2 omega naught, right? So these are all harmonically related. This is omega naught, this is twice omega naught, this is 0 times omega naught. Similarly, when k is equal to plus minus 3, you get 3 into omega naught, right? So the fundamental frequency is omega naught, and other waveforms are actually harmonically related. They are multiple of the fundamental frequency. So we call these kinds of signals as harmonically related sinusoidal waveforms. Now each of these signals has a fundamental frequency that is a multiple of omega naught, and therefore all the signals are periodic with period t, or integral multiple of t. And a linear combination of harmonically related complex exponentials can be represented now in this form: x of t equal to k equal to minus infinity a k e power j k omega naught, right? So this linear combination of harmonically related complex exponential will also be periodic, because all the components, the signals, complex numbers for different values of k are periodic. Then obviously some of these all periodic functions would also be periodic. Now for example, in this equation, let's put k equal to 0. When we put k equal to 0, we'll get x of t equal to a naught, because e power 0 is 1, and a k would be equal to a naught, so x of t would be equal to a naught. Similarly, when we put k equal to 1, x of t would be equal to a1 cos omega naught t plus sin omega naught t. Similarly, when put k equal to minus 1, we get this equation, and k equal to 2, we will get this, and for k equal to minus 2, we get this equation. So the terms for k, value of k plus 1 and minus 1, both have same fundamental frequency omega naught. Similarly, the terms having k equal to plus 2 and minus 2 have the same fundamental frequency, which is 2 omega naught. So collectively, we refer the terms having value of k equal to 1 as the fundamental harmonic component. And similarly, for k equal to plus 2 and minus 2, we call it second harmonic. And similarly, for k equal to plus 3 and minus 3, we call them third harmonic. Third harmonic means 3 times the fundamental frequency, 3 omega naught. And more generally, the components for k equal to plus n and minus n are called nth harmonic components. So the representation of a periodic signal is a linear combination of harmonically related complex sinusoid is called Fourier series representation of a signal. Now, how to determine the value of ak, the Fourier series constant, right? So in Fourier series, ak determines the magnitude and phase of complex sinusoid, which are mutually orthogonal, right? So what do you mean by orthogonal? Orthogonal means that we have cos and sine functions which have 90-degree phase shift, right? They are perpendicular to each other, so we call them the orthogonal to each other, right? So when two signals are orthogonal, it means their inner product would be 0, right? So inner product is determined by taking integral of x1 and the complex conjugate of other signal, right, x2, product of x1 with the complex conjugate of x2, and integral from t0 for one period, right, t0 to t0 plus t is called inner product, and this inner product should be 0 if the signals are mutually orthogonal. So we will use this property, the orthogonality property. So we can take advantage of orthogonality by multiplying the expression of the Fourier series by its conjugate and integrating both sides over interval t0 to t0 plus t, right? So multiplying both sides with the conjugate of the signal e power jk omega naught t multiplied with the negative exponential, and then taking the integral from t0 to t0 plus t, and let's call this equation a, right, after simplification. Here we have simply taken summation out of the integral, and then since these are both exponential functions and they are multiplied, their powers would be added, right? So after some simplification, and a of k is not the function of time, so it is taken out of the integral, right? So now we have to find out the integral of this first, and then we'll evaluate the summation. So this one, remember, is complex exponential, and its integral would be 0 when k is not equal to q, right? When k is equal to q, it is e power 0 anyway, right? And when k is equal to q, it is e power 0, which is 1, right? And when k is not equal to q, the integral of this would be 0, right? Because when k is not equal to q, this is a sinusoidal function. When k is equal to q, it is e power 0, simply 1, right? And when k is not equal to q, it is a sinusoidal function. If we expand it using Euler's identity, it is a sinusoidal function, and taking integral of a sinusoidal function one complete period, is always 0, right? If you take integral of sine wave for one complete cycle, you will get 0, because positive and negative half cycles would cancel each other. Similarly, cosine wave as well. If you take integral of cosine wave for one complete period, the positive and negative half would cancel each other, right? So this one as well is a for k not equal to q is a sinusoidal waveform, and for one complete period, the integral of this waveform would be 0. So the integral of this function when k is not equal to q is 0. Now when k is equal to q, we will get e power j into 0, right? So e power j 0 can be written as cos 0 plus j sin 0, which is equal to 1, and integral of 1 is simply t, right? So for k equal to q, the right hand side of the equation a can be written in this form, right? So integral would be simply t, and rest of the equation is same as it is. Now here we do not have any dependency on k, right? So we can simply eliminate the summation, and we can rearrange this equation in this form: aq equal to 1 upon t, t0 plus t, and this. Or if we want to write down in the form of ak again, so ak would be equal to 1 upon t, t0 plus t, e power minus jkt x of t dt. So this is the formula to compute ak, the function of Fourier series. Now to summarize, following pair of equations define the Fourier series of a periodic continuous time signal. This is the linear combination of harmonically related complex exponentials, and the value of ak can be determined using this equation. So this equation is called synthesis equation because it provides the synthesis of the signal, and this equation is called analysis equation, right? It gives you the analysis in terms of phase and frequency, and also gives you the analysis about the frequency contents of the signal. So the set of equations, a set of coefficients A, K are called the Fourier series coefficients, or these are called spectral coefficients, right? The values of A, K, for different values of K would determine what frequency components are present in X of t. Therefore, it is called analysis equation. So the coefficient A naught, for example, for K equal to 0, we call A naught. So A naught is the DC component, right? For example, put K equal to 0 in this equation, you get A naught equal to 1 upon t, T naught equal to X of t. So this is the formula for average value. If you remember, this is the average value of any signal, right? So this is the formula for average value, and therefore A naught is called the DC component. A naught is the DC component of the signal. If there is some DC offset in periodic signal, A naught would be non-zero. If it is not, there is no DC offset, the periodic signal is symmetric around horizontal axis, then A naught would be 0. So that is end of this lecture, and we will be spending a couple of more lectures on Fourier series. We will be solving some examples, we will be representing some basic waveforms in Fourier series form, so that you will have a better idea how the signals are represented as a linear combination of complex functions. And if you have any question regarding this lecture, you can send me an email given in the first slide of this lecture. Thank you very much.